So good evening, tired audience. I promise not to be very, very long. This talk is basically a case study about using GPUs to solve a physics problem. I will skip the physics, we had enough, I think. I had enough. It was very interesting for me. I'm not a physicist, I'm a computer science guy. But I cannot give you the same theory that you did before me. So, what is the topic? It's plasma simulation, and we are obviously interested in speed. This is why we came to this conference. So I will say a few words about the original problem, and then very quickly I will jump into the problems in the sequential simulation program, and then continue with the parallelization and explain what we did and what we tried and didn't work, and what we will try in the future, and give some results, preliminary results. This is quite a new project. We started 10 months ago roughly, and the idea of this project actually was born last year at this GPU conference. So this is the one year anniversary, and we are happy to present results. So that should be a moving animation. Why is that not working?
Click.
That should be automatic. Computers. Okay, so this is the setup. We have a low pressure plasma capacitive coupling, and we are interested in the non-equilibrium behavior, and especially in the particle transport, what you should see here. And I really don't know why it's not working. And just to explain what you see here, this is the generator voltage, and one end is always on ground, the other end is a sine wave. So this is the positive half cycle, and then it should go down to the negative one, which is this value. And then the electrons, which are very light compared to the ions, start to move from one end to the other. So we have some dynamicity in the system, and this is what we want to simulate. Okay, and here's my co-author, Zoltán Juhász. So if you have questions about the physics, ask him. He can explain why we want to simulate this system. So the physics behind it is not very complicated. Newton equations. The problem is that it takes quite a long time. The version we were working with had roughly 60,000 particles, 60,000 electrons, and ions, and we have an inner cycle for the sine wave, the different samples in time, and then we have a number of simulation cycles required for each basically a converged state, so we have to wait till the plasma builds up. And this double cycle and all the steps that we do in the body of the loop takes roughly from 1 hour to several weeks, depending on the conditions in the experiment. So if we have different pressure, etc., different particles or ions in the system, it can behave in quite different ways. So the question was, can we speed this up? Because running something for weeks and then finding out actually it's not converging is not a very good thing to do. It's frustrating. So this is where I joined the team, and very quickly I said, oh yes, we can. Of course, we can speed this up. And these are the situations when you turn out to be an expert or a complete idiot. Right? So, you will judge at the end which one I am. I was told that a speed up of 5 would be very nice, and a 10 would be more than fantastic. So we are not talking about hundreds in speed up. 10 is okay. So we started with a sequential C program, and working with GPUs and reaching
sometimes 1,000 speed up. And in different applications, I was very optimistic. But we had one requirement, that the original program should be kept as much as possible. So we tried to keep the code so the physicists actually understand their original code after the parallelization. So they didn't want to learn C++ or anything. We should keep to straight C and hopefully something simple that they can understand and maintain and improve in the future. Okay, so what is the first choice? OpenMP. You just put in your pragma and pray to God and it will be faster, okay? That's what I did and it didn't work. With about 2 months' work, we reached the point that the parallel program was 2 to 3 times slower than the original sequential. So that was the complete idiot case. And I first didn't understand what happens. And then it turned out that actually this simulation, as simple as it seems, it is a pretty complicated beast when you look at the memory access patterns and all sorts of funny things like random number generation, etc. So OpenMP is basically not usable here. It's a very easy to parallelize system on the geometric front, but internally it's very, very bad because of the cache invalidation effects. So we very quickly gave up and decided that even if the OpenMP works, with normal systems we can get maybe a speed up of 4, 8 maximum, not more than that. And of course 10 was the goal, but really that would limit the speed up of the system forever, so you cannot get more than 10 normally. So since it didn't work and we would be limited anyway, we decided to change tack and use GPUs, hoping that we would get more speed up and we would have basically a way to run in the future. And this is what we started. And again, that seemed quite simple at the beginning, but there were quite a few interesting problems appearing on the way. So first of all, this simulation is a particle in cell simulation, which when you run in parallel is based on a geometric partitioning. Right? These are the cells, and you have particles randomly anywhere in the cells. They move around based on the acceleration or the force, and typically these are MPI implementations. If one particle moves out of the cell, you push it into the other one, there's some boundary exchange, etc., etc. And that's fine. We understand how that works. The problem is we had to simulate a one-dimensional problem, and the one-dimensional grid, this geometry, was 256 cells, basically. And our GPU card has 4,000 cores. So it didn't seem a good fit, right? Giving work for 200 threads and the other 3,000, I don't know how many, is just lying around and laughing at the others is not a good idea. So we had to reconsider the entire structure of the code to be able to give work for everyone in this GPU. And what's more, if you want to run efficiently on a GPU, you have to have much more, or many more threads than cores. So with a 4,000 core machine, you would have 100,000, at least 50,000 threads, or more than that. Luckily, in this application, we had 60,000 particles, electrons and ions each. So we decided that actually we would go straight to one particle per thread approach and see how that works. So that was the first idea. I don't know why that is changing. And I forgot to say this, but on a new Pascal architecture, we can have 80,000 resident threads, which means that will be always in hardware. You never have to reload a thread or worry about switching context. It's there, it will run forever. Okay, so we reached the area what we call extreme scale programming, and someone was talking about exascale. person from Intel. Is he still here or left already? Okay, so exascale means you have hundreds of thousands of threads or even millions of threads. And the problem is not the architecture, the problem is the algorithm. How can we make something run with hundreds or thousands or millions of threads? So that's an interesting problem. So we created the first implementation, basically mapping each step of the internal simulation core, or what do you call it? I have to go back. These steps, these are the sequential steps in the body of the innermost loop. We mapped each box into a kernel, a CUDA kernel, and you can see here the execution. So that's the electron move, this is collision, density calculation, ions, ion collision, again ion density, and then solving the Poisson equation and starting again and again. And it works good, fine, but not very fast. So the first attempt was, I think, twice as fast as the sequential one, and the card is obviously much more powerful than that. So if we look at the kernels, each kernel will read data into the chip from the device memory, do some very little computation on it, modify some data and store results back, which is not a good recipe for high performance. So it turns out that each of these kernels are memory bound. So it basically doesn't matter what we calculate, it will always be the memory bandwidth that will stop the system. But what's even worse, we don't even reach the bandwidth performance we would expect. So we are way below the real performance. And this is a list of all the potential performance issues that we can find in such a system. So in this case, we have too little kernels. So each kernel takes about 5 to 10 microseconds to launch, and maybe they run for 20 or 40 microseconds. So not much work for each launch. So we cannot amortize the kernel launch. And as I said, it's memory bound, so the compute intensity is very low. And in this particular implementation, the Poisson equation is solved on the CPU, so we have to copy data back and forth between the GPU and the CPU. And the reason for using the CPU for the Poisson is that the sequential algorithm is very, very fast. It's a two-diagonal solver. It solves the system in 10 microseconds. The CUDA version would run about for 100 microseconds. So even with the copy, it is roughly the same or better performance than the GPU implementation. So the question is, can we make this more efficient? This is a breakdown of the execution time of these kernels. You don't have to memorize it or anything, it's just a demonstration of the profiler output. If anyone is interested in measuring the performance of a GPU program, there are tools to do this in a very detailed way. And the important thing is the bottom, that with some optimizations, we actually managed to get down to 200 microseconds. And of course, the numbers don't say too much. The original innermost loop ran for 3,000 microseconds. So 200 is over the 10 speed up targets that we were hoping to reach. So that's quite nice. And eventually we got a speed up of 20 with this implementation after some optimizations. So the original implementation code, which was 1 hour or even more, in the 1D case is now down to 3 minutes, which I think is quite good. And it's probably not the end of the story. We will be able to make it more efficient. This slide is just here in case someone later will look at the slides. This explains how you can measure the memory and compute intensity of a kernel and compare whether it's memory bound or compute bound or latency
Mm-hmm.
bound. And if someone interested in it, I can explain later what this is. So let's look at some practical optimization possibilities. This is the original current implementations, and the green lines designate the memory load and store operations. So each kernel will fetch data, modify or compute and store data back. If you can fuse these kernels, so we can make all the electron related operations move into one kernel, all the others, sorry, these are ions, I just spotted a mistake. So the brown is ion. Then hopefully we only load data once, do a lot more computation and store data back once. Okay, so this gives quite some improvement, at 20% more, and with the most advanced GPUs we can run concurrent kernels. With the Pascal architecture I think it's up to 32 kernels that we can run at the same time. So the hope is that electrons and ions can be executed at the same time independently, because they are basically don't depend on each other. If they collide, as they do, we can do that in the next iteration step. So inside one iteration they can be treated independently. So I was hoping to see something like this, two CUDA streams executing electrons and ions at the same time. Then we do a stream synchronization and solve with Poisson. But we get something like this. There is some overlap, but not much. And this is an architectural issue. If you use Kepler architecture, even though it supports concurrent kernels, it doesn't really do it properly because the thread scheduler inside is not fully concurrent. But if you use Maxwell or Pascal architecture, they will run in parallel. So I just wanted to point out, maybe someone's interested in that. Okay, so there are many options. I would highlight a few more optimization possibilities. One is to use shared memory. We already done that, but it's not in the results yet. The field, the electric field, which is used for the interaction calculations, can be loaded into shared memory, and then all threads can read from a much faster memory. I can't remember the number, how much performance gain this will give, but it's measurable. It's quite important. The other one is the random number generator. We started off with a CUDA random generator, which is surprisingly slow, and we don't know why. It should be much faster than actually it is. So in a new version, we changed to a different random number generation, which is much faster to initialize and much faster to generate the numbers. So that also improved the execution time. And the third one is to use a better Poisson solver on the GPU. The QSparse library has a very general tree-diagonal solver, which is not very fast on the GPU. Maybe because our system is too small, so maybe we will need to write a specific implementation for this particular one. Okay, so finally the results. I already told you that we have a speed up of 20 for the one-dimensional case. We are down to 3 minutes from an hour. And obviously the main question is the accuracy. Is this any good? Because if you produce junk in 3 minutes, that's not a very good result. So the good news is the results look quite fine. The little dots and the line are the original sequential code and the GPU results, and they are quite nicely on top of each other. And currently in the pipeline are the other optimizations. So we are experimenting with the fused and concurrent kernels. The fused one is working on my laptop, but not working on the fastest card. So we also have not a number error for some reason, and it's very non-deterministic. So we're fighting with that, and hopefully once that is fixed, I think we will go down to about speed up of, not down, up, speed up of 40. So there's another factor of 2 probably in the speed up. Another not playing animation, I know why. We forgot to copy the video and it's not embedded. Sorry, my mistake. Which one is it? I will play it from the pen drive. But the final sentence is that while we were doing the one-dimensional simulation, a 2-dimensional version was also produced, which was not planned really, but sort of as a side effect, just happened to be written, which is a very good result. That was written by Peter Hartmann, and the speed up is quite good. This is a non-optimized, really first version, and speed up of 90 at least. So a program which was running for 3 months can now can be executed in 1 day, and produces this video which I couldn't play properly. So I'll stop this and show you the real video if I can. Ooh. I need a file manager. Okay, so this is the result of the simulation. Sorry, can you tell us what this is?
So actually, we always try to generate low ionization degree plasma. So it's a neutral background gas, and you have 1 electron and ion per 1 million neutrons. And here, the lower electrode is powered, so you have a sinusoidal voltage of a few hundred volts, or 160 volts in this case, while the upper electrode, which you see this white line, is ground. And in this gap, you generate this plasma, and the movie shows 1 cycle. So you can see these flashes correspond to the peaks of the voltage where electrons get accelerated, multiply, ionize the gas, and then the whole system diffuses to the walls. So this is a highly non-equilibrium, rapid change of the densities, and I mean, just why we do is a wide range of applications. For example, in chip manufacturing, this is very widely used to etch silicon or silicon oxide. So this kind of home business story, because in Silicon Valley and other places, these technologies are used to produce the chips, which can help further optimization of applications. Thanks.
Okay, thank you very much.
So we have time for a few quick questions. Yes, everybody wants to go. Yes, 1 question.
Make a code 20 times faster is a really great result, but can the physicists still understand the
Yes.
code? Yes, they can.
Yes, the kernels, the internal code is basically 90% identical to the sequential one. So it's more just restructuring, but the actual computations, so the physics part is untouched, basically. And I'm quite confident that 20 is not the end. So 50, I think, is achievable, and the importance of this is the best speed up number we know from literature is 20 for millions of particles. And if you have 100,000 particles, obviously their speed up is lower because there's not much work for the GPU. So if we can get to 40 or 50, that would be pretty much a world record.
1 more.
Actually not related to the physics. You said that it took you 2 months to get a parallel code that was 2 times slower.
Yes.
So after that failure, how long did it take to actually write 10 times faster code? Just to see how much you spent in the 3 months on that.
The first part of the question, the 2 months for the slow code, actually writing that code was 1 day, and figuring out why it was so slow was 2 months. And writing this code was 2 months. And measuring the speed was 2 days. So this is much better. Can I just add one more thing? Actually, it's a very good question. So the problem with OpenMP and maybe with other high-level languages is that you take it for granted that you compile your code, you run it on a state-of-the-art hardware, and it will run faster. And if it's not running faster, you cannot do anything. You just accept the fact that that's it. But if you go low level, and if you know how the architecture works, and you can control from your program how to do things and when, then you actually understand why it is slow or whether or not it can be faster. So I'm not saying high-level programming is bad. I think it's very good. It has its place. But if your top goal is performance, you really have to understand what the system is doing at the low level. Otherwise, if it's not performing, you don't know why. And you just go into the corner and cry. Yes, I did that with an OpenMP, and this is why I've given up. Okay.
Okay, so let's thank the speaker again.